Okay, I think we're ready to go now. Hello, everybody again. My name is Joanne Kwan, and I'm a Senior Research Manager at CIRIA Research Manager, and I'm also the Project Manager of this report we're going to talk about today. I just want to welcome everybody to today's webinars to launch CIRIA report, the new CIRIA report C812, Geophysics in Ground Investigation, a client's guide. I'm so happy to see so many of you today, as obviously it's a very popular event, and we have over 200 people registered. But before I begin, I just want to cover a few sort of housekeeping points. This webinar is being recorded, and the presentation and the recorded webinar will be made available to all delegates after the event. We are all in listen-only mode. If you have any questions or any problems with IT issues and anything else, please raise your hand or put a note on the chat box, and we will hopefully CIRIA colleagues will be able to help you. As you can see from the presentations, we will have from the program, we will have presentation first and the question at the end. And please type your questions at the Q&A box. And also, if you, when it's a question time, if you hear or agreed with certain question that people asked, please put your thumb up. And also, if there's anything that you want to share with us on that resources, etc., you are, please share it on the resource. Please share it in the chat box. And obviously, we are seriously very keen to hear about your experience with the webinars. There will be a short poll at the end of the event. And if you also want to receive CPD certificates, please also complete the form. Also, if you can share your views and experience with us, that'd be great. And hopefully we'll be finishing at about 3:30. So for those perhaps who are less familiar with CIRIA, CIRIA is a Construction Industry Research Information Association. We're about 65 years old, and our focus has always been working collaboratively with industry and other parties to improve construction projects practices. And we have published over 700 good practice guidance reports ranging from SUTS manual, rock manuals, and also contaminated land. And also we have a very strong record in producing reports, good practice report on geotechnical issues and asset managers asset manager subjects as well. And on top of reports, we also do on average deliver about 50 events, from webinars like today's event to conferences. We also participate in exhibitions and debates. So this is just a sort of snapshot of all our members. At the moment, we have about 80 members, and you can see it's from a very diverse range of backgrounds, from academics, consultants, clients, contractors, major government bodies, and local authorities as well. Okay, so going back to what we are talking about this afternoon, it's all about, we're going to tell a little bit more about the new report, C812. Although the title of the report actually say geophysics, good practice geophysics for ground investigation, a client's guide is also obviously very relevant to other specialists who work in the subject, like consultants and contractors, because geophysics is actually been around for a long time, but I think a lot of people still think that there's a bit of a black box with it about the whole subject. And hopefully this new guy will demystify some of these confusion and demonstrate the benefit of applying more ground more geophysics in ground investigation. And obviously, this project will not be possible without our help and assistance from the Project Steering Committee and the funders. And obviously, we're very grateful for the help. So going back about geophysics and what we're talking about today, as we all know, geophysics are being used in ground investigation for a while now, as I just said. It's a very good method because for most people, you know, when you try to understand what's in the ground, it's actually a very difficult task. Most people might take samples or do sort of measurement, but as again, you know, it's quite expensive and it's very difficult to find a way that you can easily have a very holistic view on the ground. And geophysics is perhaps quite special because the use of those different techniques can actually look at the whole site in a wider context. It's obviously not going to give you every answers for your questions. It's not going to know exact everything on the ground, but it certainly helps a lot, and especially if we can use this with other methods that hopefully will improve your understanding of the ground enormously. So this is the aim of it, because as I said, I still feel that there are still quite a lot unknown in a lot of practitioners are still a little bit scared about geophysics. The aim of this project is also demonstrate good practice. And in when we talk about good practice, C812 is actually not the first guide that CIRIA produced on the subject. About 22 years ago, CIRIA published C562, which is a still very good report. But we feel that obviously with 2 decades gone, we need to update this report and also with perhaps new techniques and new case studies. I think the aim is from the new report is we're trying to understand that if geophysics is still useful, is it still being used? Has good practice changed? If so, what is good practice? And is there any way that we can apply geophysics in more construction projects? So this is today's program. We have some very interesting speakers and also explaining to you what the report will be like, and then the third presentation we're talking about more about cost-benefit analysis, because I think that's very important when people decide what method to use, and followed by question discussion. So these are our speakers: Oliver Chris from ACOM, Charlotte Oshers from RSK, and Jim Whitley from Ekins. So I think I'm just now going to stop and introduce the first speaker, Oliver Chris, and he's going to talk about the pros and cons of using geophysics in ground investigation. Over to you.
Thank you, Joanne. Hi, I'm Ollie Crisp. I'm a technical director at ACOM and head up our in-house geophysics team. So use of geophysics in engineering is increasingly accepted and even expected by many of our clients, though it's still relatively poorly understood, underused, and often not used with confidence. Geophysics for engineering involves a broad range of tools used to solve diverse problems with in different environments, so it requires a level of knowledge and flexibility to be used effectively. Though often treated as such, it's not a true contracting service and is best used when fully integrated into investigations. There are work areas within engineering where use of certain techniques, particularly GPR, is relatively mature, with work phased appropriately and methodology and output standardized, and often done by technicians familiar with a single use of the tool. The development of that phasing and use is invaluable, and yet even small variations in survey requirements can require a totally different approach to gain effective results. In some cases, this can take contractors outside of their comfort zones and lead clients to lose confidence and faith in these tools. To my mind, there are 4 key things to learn with geophysics. It's not just what can work, but the limitations of the techniques, which is important. What doesn't work and why? Survey design, looking at the appropriate resolution, depth, environment, and pairing techniques to most closely match the information you need. To make investigations pay their way, we need to look at when and how to use them to best manage cost. And to get the best value out of the information, we need to integrate it into the projects so the data is fully utilized. So hopefully we'll move on to the next slide in a second. Let's try again. Okay, so what is geophysics? It's basically just a toolbox. It measures different physical properties of the ground or structure. So commonly used techniques include acoustic, so seismic techniques, electrical, electromagnetic, magnetic, and gravity. Broadly, you can use these techniques by area for linear profiling, or for resolution with depth using downhole, in-hole, or cross-hole techniques. These techniques can be applied for reconnaissance surveys over broad areas or long distances, over localized site investigations, or for targeted detailed investigations such as failures. A second, just move on to the next slide. So why should we use it? If you consider traditional intrusive GI, you're looking at high quality information, but a very small sample size, and it's discrete information, so it's not necessarily representative of the materials around. Geophysics gives a lower quality information. It is still factual, but it's not as high quality as intrusive GI, but you can get a very large sample size quite quickly, and that gives continuity of information. Though we do lose resolution with depth in this, as I mentioned before, you're looking at wireline techniques or downhole techniques. Geophysics is critical in planning GI on sites where there's a heterogeneity in site conditions expected. If you consider our linear infrastructure, things like roads, rails, tunnels, pipelines, etc., you will inevitably encounter changes which will impact support, which a regularly spaced GI will often miss. Having spent a lot of time looking at GPR data, for example, on the road and rail infrastructure, I've seen the impacts of this type of issue in the form of localized settlement, which requires regular long-term maintenance. In a time where we're aiming for minimum maintenance strategies, it's no surprise to me that 2 of the main funders of this guide were National Highways and Network Rail. So why use geophysics? The first use of geophysics, to my mind, is to identify and target change. I often get told that geophysics is great because it joins the dots between ground investigation. For me, that does it a disservice. Used well and at the appropriate time, it informs the intrusive GI, allowing it to be targeted. The result of that is you get less holes, you get a more representative sample, you get increased quality in your ground investigation, and if you feed your GI back into the data, you can improve your ground model and get engineering properties out of the data, depending on the techniques being used, of course. That may mean more cost in the GI, but it may also mean less. What it does mean is you get a reduced design risk. You also reduce the construction and maintenance risk after you've built the structure. And you can also reduce the program risk by identifying changes early. As such, you reduce the cost risk and the risk of escalation throughout the project. The images shown above are on the slide for an EM survey of a site which included both variations in landfill and contamination issues. On the left, you can see how regularly spaced boreholes pick up the general trends within the site. On the right, though, you can see how a targeted investigation provides a more representative sample of specific changes with a reduced number of boreholes. With techniques such as this, we do have to be a bit careful, though, as the changes present can be caused by a range of factors. So all changes may not be of significance. So other reasons for using it is to look at things like the engineering properties of the ground. For example, the image shown is for an MASW from MASW data. That's multi-channel analysis of surface waves, and the data you're looking at is a profile showing S-wave velocities, and these correlate with stiffness. From that, we can integrate GI results and calculate things like Poisson's ratio, shear modulus, or Young's modulus. If you're looking at seismic refraction, you're looking at P-wave velocity, and that actually has a correlation with ripability. If you're looking at electrical resistivity, for example, most of the changes are based on moisture, so moisture variations within the soils or rock. And you can use that for looking at things like earthing or corrosion potential. And that's alongside the more standard uses for things like rock depth, weathering, and correlations with material types. If you're looking a little bit deeper, you can use electrical techniques as well for things like mapping aquifers within rocks, either for water resources or for the impacts on structures, such as tunnels, where things like water may be invaluable. If you're looking at the structures on a shallower level, if you're looking at structures, you can use geophysical techniques to map up reinforcement arrangement, dowels, tendon ducts, or look at construction thickness and condition. Slides are moving along. So where might I use it? There aren't many areas of engineering where these tools cannot add value. As a brief overview, consider environmental surveys, for example. You can look at things like contamination, landfill, pits, etc. If you're thinking about geohazards, again, we can map up issues associated with landslips, where you get increased water content within the soils which increases the chance of slope failures. Also things like solution features or faults. Engineering properties, as I listed previously. We use these tools for asset management, things like high-speed investigations of the rail and highways network, where you can map up material construction, condition, and support. You can use for assessing buried features, remnant structures, such as foundations, footings, archaeology, cellars, or air raid shelters even. If you're looking for buried hazards, we use these tools for shafts, adits, UXO, tanks, and utilities, which is an industry in itself. When looking at structures, you can think of sea defences, bridges, tunnels, dams, historic structures and buildings. Or for more specialist NDT, you're looking at similar techniques, but at a different scale. So what are the problems with these tools? Historically, geophysics has been viewed either as some sort of magic box or something that doesn't work, or that is a risk to use that you may be criticized for because you add cost to a project. Intrusive investigation results were often not provided and used to test to see if geophysics worked rather than used to help interpret the data. It is often considered an expensive or an additional cost, and it can be. It is not a low-cost service, as data takes time to collect and time to interpret. Historically, it's often been used to solve problems after more traditional methods have already failed. At that point, it definitely does add cost and may require further intrusive investigation to verify it, leading to cost escalation. So you can see why it becomes unpopular. Timing changes that balance, with early use allowing GI to be targeted and potentially reduced, as we've discussed before. As such, it can reduce the overall GI cost. program, again, it can add to program as it is an extra phase of investigation. However, surveys are typically small scale and non-intrusive. So similar to topographical surveys, it can be done pre-CDM regs. This allows the surveys to be phased early, supporting a targeted GI program and potentially providing data to support preliminary designs. But to do that, it has to be considered and commissioned earlier in the project lifecycle. On sites with difficult access, such as rail, a rotary rig, for example, may only be able to access track effectively on, let's say, a Saturday night due to issues with limited possession times, vehicular access to track, and time and machinery, and the time and machinery it takes to get a rig in place. Geophysical tools, in contrast, are handheld and relatively mobile. So those still limited by short working windows can often still be effectively used and are less impacted by cancellations. As such, in some circumstances, programs can be dramatically improved, particularly where intrusive investigation is reduced. Perceptions have changed significantly over the last couple of decades. It is becoming increasingly accepted, and for some clients, actually expected. Intrusive results are more commonly fed back to support interpretation, but it's still often not considered. A lot of that comes from the confidence in understanding of the tools and where they can be used on projects, how to use them effectively. This guide should help with that, but also consider asking a specialist for support and advice when considering these tools. So, how we scope and use it. When we do scope geophysics, we need to consider and give information on things like the resolution, so the scale of features you need to resolve, and the depth of investigation, as this will impact the tools which can be used and how we set up the surveys. The environmental conditions around the survey area and ground conditions, both of which may be impacted by things like the timing of the works, or for that matter, other works happening alongside them. Think about cross-correlation of techniques, measurement of different contrasting properties, as that can give confidence in findings or highlight increased complexity of ground conditions. As an example, I've had situations in the past where 2 and even 3 different techniques give different results for rock depth. It's easy to assume from that geophysics doesn't work. And though I understand that, it's not actually correct. What it shows is that the ground conditions, in this case the weathering profile of the rock, is highly complex, such that you could classify the rock at different levels based on the interconnectivity of water particles from the electrical resistivity, the S-wave velocity or the P-wave velocity. When you consider borehole data, where weathered materials transition into rock, it isn't always that obvious there either. As such, it's always good practice to utilize more than one geophysical technique. As I say, if all the techniques match, it gives you very good confidence in the results, but where they differ, you get it identifies that complexity. We also need to consider the timing and phasing. As you think about allowing the changes in survey methodology to optimize the data quality and minimize the cost in geophysical surveys. A trial on site may identify that one technique works particularly well, or others don't work at all. Use of preliminary findings to consider to facilitate use in scoping and targeting GI, but also consider things like lines of communications. So if you can establish these well in advance, that allows management of change based on your conditions. Also ensure that final reporting integrates the geophysical findings with the intrusive results to optimize your ground models. Scopes, again, are definitely improving with more information on the goals of surveys, which allow consultants to price them as effective investigations. But working on both sides of the table, it can be difficult to compare apples for apples. Just one thing to note here, though. As a client, if you don't include geophysics in a scope, particularly for a competitive tender, geophysics is generally not put forward, even if it has been considered. That's either due to being ruled out as a non-compliant tender, or that risk that your tender will be ruled out, or through fear of cost additions ruling you out of contention, So even where it has been considered, it's quite commonly removed from a tender response. The intent, of course, is that it's hopefully to be raised once the bid has been won, but that doesn't always happen. So move on again. So how can this guide help with that? The aims of this guide is to develop a more mature industry. What we're looking to try and do is improve knowledge, help you with clients understand the strengths and limitations of the techniques. We want to identify opportunities, demonstrating the range of common uses, increase the effective use, showing examples of good practice that you can follow, align expectations to understand how the tools can be used and what their outputs actually mean, improve the procurement and timing to maximize the benefit and value gained from these tools, facilitate flexibility in your surveys through good lines of communications and change management, manage cost and cost risk, not just through the surveys, but through design, construction and future maintenance, and raise the quality of output, not just for geophysics, but as a whole ground investigation package by integrating these tools into projects and making them more common usage. Finally, from me, we should not be considering ourselves as innovating by using these tools. We are just applying good practice. Thank you.
Right, thank you, Oliver. May I remind everybody again that if you have, please type your question in the question box, and if you like others attendees' questions, please click thumb up so that we can perhaps focus on the more popular question at discussion time. Now the next presentation will be given by Charlotte Usher, Principal Geophysicist at RSK. She's obviously the most appropriate person to tell you a bit more about what C812, the guide contains, because she is the major author of that report. So over to you, Charlotte.
Thanks, John. Welcome. So I'm Dr. Charlotte Usher. I'm technical lead at RSK Geosciences, and as John mentioned, lead author of the CIRIA C812 document. Apologies. This new CIRIA guidance was published last year in December. It's, as mentioned before, trying to update on the previous CIRIA guidance, C562, that was published back in 2002. This came about because during talks produced by CIRIA on innovation in ground investigations, it was highlighted that there was a need to better demonstrate to people the many tried and tested ways that geophysics could be applied on sites, ideally through a set of examples of its use. And while the science in C562 is still relevant, there's obviously 20 years of advancement, over 20 years of advancement in the technology, in the use of techniques, and all of this overall meant there was need for an update. The aim of this new document was to therefore provide this overall update on the content of C562 to reflect the current practice, and to provide a better and more up-to-date tool for those that were looking to scope or request geophysical investigations on their sites. It also looked to provide those people with a set of real-world examples for specific geophysical applications. The new guidance highlights examples of good practice, as well as areas of the survey that potentially could have been improved, with the overall aim to try and stop people thinking that geophysics is just too expensive to bother with, or black magic. So the guide is split into 5 main chapters. The first 2 and the final chapter are relatively short in comparison to chapters 3 and 4, which contain most of the information and were a major focus of the document. Presentation within the document was also a key focus. So we've used call-out boxes within it to highlight key elements or examples of good practice at each separate stage of the survey, and also any particularly relevant warnings that we felt were necessary to convey to people. I'm going to briefly just go over the content of the document and hopefully highlight some of the elements that should be of use, hopefully. So chapter 1, that defines what this guide is for, along with what we actually mean by geophysics, what that actually is. So it defines when and where geophysics should be used within a ground investigation. So when you think about using geophysics, with a real emphasis on the fact that it's, as Ollie mentioned, most effective when it's considered early on in the planning stages. It considers even when geophysics might not be of use on a site and discusses around that as well. And also includes a discussion on the potential cost benefits of using geophysics on your site effectively, which Jim's going to discuss in the next. There is an overview of the roles and the qualifications of a geophysicist, particularly what we would define as a competent geophysicist, which is a term we use throughout the document. And it also finishes this section with a client's guide to procurement, which basically details what a client should expect to receive at each individual stage of the survey, so they know what to expect, and it makes them more confident to then ask questions during the process. And the guide aims to be realistic and honest with its descriptions. Chapter 2, this is an overview of the common practice that we use now. So it discusses the different stages of the geophysical survey in more detail, right the way through from design of the survey through to data interpretation. So it's talking about what should be expected at each stage of the survey. It highlights any relevant good practice that should be being put in place. And it also talks about any sort of further considerations or issues that may occur at each stage. So, for example, within the survey design stage, it discusses the desk-based elements that you would undertake during a survey, as well as things like the pros and cons of a site visit, for example. This chapter then aims to kind of explain, well, it aims to explain common terms that we as geophysicists will use fairly regularly, things like inversion, but that might not be necessarily as well understood by non-geophysical practitioners. And then it finishes the chapter with a summary of all of the advances that have happened within the last 20 plus years since the publication of C562. So this includes things like 4D measurements, impulse GPR systems, integrated GPS. Chapter 3, this discusses the geophysical techniques that we considered the most commonly applied within near surface ground investigations. And a big impact of this, big aim of this chapter was to be less science heavy and make the information more accessible. There's a number of texts that are already in existence that will provide that information should people want it. And we tried to condense it down into a more readable amount. The start of the chapter has more of a focus on how to choose the correct technique for a survey. So looking at the things that you would need to consider during that, which is aided by tables that are based off existing ones in texts, including the British Standard Code of Practice for Site Investigations, BS 5930. But the content's slightly different as it's designed to marry up with the techniques covered in chapter 3 and the applications covered in chapter 4 so that it links in with the rest of the document. There's also a lot of emphasis on the fact that the descriptions within those tables are obviously site and technique specific, particularly when defining the effectiveness of those techniques. It also splits up the common geophysical techniques into 4 main areas. And the techniques within these are grouped by those that either measure the same or a complementary property, and that use similar methods of data collection. So, for example, all of the electrical methods that are described all use electrodes for measurements to acquire data. Each section defines kind of the basic science behind the method. It talks about the key applications of where you would use that sort of method and includes photos of example equipment in use use and relative diagrams for each technique. Any key geophysical properties that are measured by that method are represented graphically rather than as a table of numbers, and they're color coded by material type so that you can better visualize the ranges that can be of each property and how those overlap. You can see an example here shown for S-wave velocities, and these sections also for each individual technique will highlight the main advantages and limitations within a call-out box to make them more obvious. It describes the basic theory behind each technique as well as the typical methods of data collection and presentation. Right, moving on to the next chapter. This is the longest section of the document. This is where you will find the examples split by application type of the use of that geophysics within a ground investigation. These applications are split into 4 rather broad areas. So you've first got geological applications, then physical property determination, environmental, and then finally buried artifacts and hazards. The important thing to note here is that most of the included examples consider targets that are within the top 50 or so meters of the ground, although more typically it's the top 5 meters. So it doesn't include deeper investigations such as petroleum or ore. It doesn't include water or offshore applications. It doesn't include radioactivity or radioactive waste, and it doesn't consider small-scale structural or non-destructive technology applications. These are quite niche and they're covered in documents elsewhere. So each main application is then divided into further subsections, as is shown here for the geological applications. Each section then discusses the different sort of targets that we might be looking for. So for example, in solution features, it will discuss things like cost. It'll discuss the typical useful techniques that we might use where appropriate, if there's any sort of limitations we should expect, and also where things like trial surveys may be useful or have been successfully applied. And each of these sections then contains at least one, if not more, case study, or in some cases, example data. And these case studies were all structured to contain the same sort of information. So first, we have the background information. So this gives a bit of context to the project. It discusses the site and why we would be there to collect the data. This is followed by the survey design. This covers the sort of techniques that were used, information such as whether or not it was a phased approach, whether a trial survey was used, the type of kit that was used, the frequencies, if relevant, the length or direction of any survey lines where appropriate, and any other information that is relevant to that investigation. And finally, the last part discusses the survey findings. So this is going to contain the main interpretation from the geophysical investigation. This includes any supporting evidence, such as boreholes. It highlights where any techniques have worked advantageously, any good practice, and also any limitations or anywhere where maybe there might have been improvement. The data that is presented is shown with errors or uncertainties highlighted where provided as an example of using good practice. And any captions or notes that are associated with the figures try the best to describe the reasons for why the figure has been interpreted in the way it has, to make it a bit clearer, basically. The second application section discusses the use of geophysics for determining properties such as geotechnical properties of materials. Obviously, the geology of the UK is quite complicated, so assumptions on homogeneity are usually inappropriate, which is where we have to use these sort of techniques. In some of the sections in this chapter, we had to use data examples rather than case studies. Some of these topics were a bit sensitive, people not really wanting to admit that they had corrosion measured on their site, for example. In other cases where it's been appropriate, we've anonymized the example that's been used. This section also contains a brief description on borehole studies. And as mentioned earlier, this comes under one of those topics that's quite a wide subject area. It in itself is a document, but it needed mentioning as it is applicable to ground investigations. And in cases such as this, where there are other documents to refer to, relevant guidelines or standards in existence, they've been referenced within that chapter. The next application area is the environmental applications. This focuses on materials that may be hazardous to the environment or human health, or leakage of fluids from boundaries that should otherwise contain them, which can either involve detecting the fluid itself or the containers that they are or should be in. And again, there was a bit of overlap between some of these topics, and where that's appropriate, the other sections have been referred to. And the final application section discusses buried artifacts and hazards. So this is arguably one of the more common applications that we have of geophysics. It covers a lot of near surface obstructions that could either pose a risk to existing infrastructure or any proposed new developments. I mean, no one likes to hit anything they weren't expecting when excavating. That can potentially slow down progress on site as well as increase risk. There's a lot of case studies involved in these. Some of these have multiple case studies within the sections. So I'm thinking this is probably going to be a chapter of interest to quite a lot of people. The final chapter of the document, chapter 5, this introduces the techniques that are considered more non-standard. So we're trying to look at these from both the benefits that they can potentially provide, as well as the challenges that they could still face. Some of them are being applied more regularly to engineering or environmental investigations already, which includes use through some of the applications that were discussed in the previous chapter. And then some of them are still in the development stage for commercial use. We separated the techniques out into 3 main sections. The first discusses the physical platforms, which is the mechanism from which technologies can be used. And this largely covers drone technologies. Again, some technologies like drone magnetics, they're so well established, they already have their own specific guidelines. One was published back in 2022. And again, these are referenced within the document. It also discusses some of the issues that we are facing as this technology improves further, such as the changes to the rules over drone flights as drones are able to fly further and further away. The next section discusses more specific technologies. So these are listed in an order that was discussed at length by the project steering group, from ones that we considered more commonly used or more advanced in technology through to those that are, again, still in commercial development. It tries to unbiasedly describe the use of these technologies and the potentials for future use. So technologies such as controlled source audio frequency domain magnetics, also known as willow stick, and synthetic aperture radar, they're well-established techniques with being increasingly used commercially, basically. Particularly the SAR technologies. Distributed acoustic sensors and cosmic ray muon technology are also being increasingly applied within engineering and environmental applications. An example shown here is a use of cosmic ray muons being used to identify shafts in the roof of a rail tunnel. And advanced gravimeters covers quantum technology, as well as accelerometer sensors, like those that are used within smartphones or advanced seismic equipment. These are still in development stage, but each have the way to potentially change the way we use microgravity technology. And finally, the last section is to do with data management. So we are obviously starting to use more 3D, 4D data collection, multi-channel data, nodal systems, and collecting this in the same way we would have collected 2D data just doesn't work. Some of these systems can produce terabytes of data from just one survey. So this part of the chapter discusses what we need to do with these increased quantities of data. looking into things like machine learning as well, and how that's developed in terms of auto processing, which is something that's going to be needed more as these data sets continue to increase. So in conclusion, this guidance, it's aimed not at the practitioners of geophysics, but at those looking to commission a geophysical survey within a ground investigation. It's aiming to look at geophysics in a clear and honest manner, giving you a description of the range of tools that you have available, the information that those tools could apply, and how to best make use of that information. And this is done through descriptions of the survey techniques, as well as a number of case studies and examples of good practice. And we hope that this guidance will help make people feel more confident in the use of geophysics within their next project. So consider using it early on in your project for the most effective and potentially beneficial inclusion of geophysics on your site. Thank you.
Thank you, Charlotte. The final presentation will be given by Jim Whiteley, Engineering Geophysics Lead from Atkins Realist, and he's going to talk about how geophysics could actually lower in costs and add benefit to site investigation. I'm sure that's of interest to a lot of you guys. Over to you, Jim.
Thanks very much, Joanne, and thanks to CIRIA for the opportunity to talk today alongside the chair and the lead author. It's very exciting to be here to talk to you. I want to talk today a bit more about some of the specific applications. I mean, we've got this fantastic document, which I'm sure you're all going to go out and buy and read after this presentation. And we've heard some really fantastic background from Oliver from ACOM. I want to talk to you specifically about a case study, one that I was involved with, that really, I think, highlights some of the ways in which we can apply geophysical data to get the absolute best out of it for the project outcomes. I initially worked as a contractor many years ago, going out and collecting this data, where my main focus was on data quality, making sure that we were getting something that was going to be useful. But I very rarely had an opportunity to see how it was being used in the project lifecycle. And now that I'm a consultant and I sit trying to make sure the specifications are right for these projects and really working to integrate these data, I'm far more concerned now about the cost and benefit and what value these types of data are bringing to projects. And that's what I want to talk to you about today. So I'll talk a bit about that before I move on to this specific case study and wrap up with some conclusions. I always start my presentations with this slide, which very much just gives a broad overview of different types of remote sensing. Broadly speaking, we've got on the top there remote sensing information that's been gathered across the years and the major developments in remote sensing. And along the bottom, we've got corresponding developments in near-surface geophysics. And I always think it's really interesting to remind ourselves that we've been interested in three-dimensional data relating to the surface or the subsurface for over 150 years now. The top left image there is a stereoscopic image, which is archived in the New York Public Library from the 1870s, showing basically a 3D image of the surface taken from a hot air balloon at the time. And we've seen innovations in remote sensing and imaging happen throughout time. We've got a fantastic archive of World War II imagery, and of course the launch of the spot satellites and other remote sensing observation satellites in the 1990s, right through to where we are today, which is that a situation where the cost, both in terms of computation and financial cost of acquiring remote sensing data from things like drone platforms has almost become bespoke for projects. And one of the things I'm really interested in is in how this has captured the imaginations of ground engineers, and it's almost become just completely routine now to have these types of data. And we've seen similar corresponding developments in geophysics. So back from the development of digital geophysical methods in the early 1900s through to computerized applications of things like data inversion, 2D imaging in the 1990s, and the development of software, which we still use today for lots of programs, lots of processing of software, three-dimensional applications, and then finally things like four-dimensional geophysical monitoring coming online in the last decade or two. And these two types of data really interest me because when we think about ground investigation and what we're trying to achieve using different types of data, we really want to try and expand on the quantity, the type, or the quality of information about the ground and what that can tell us about the ground and what's relevant to our design of the infrastructure or asset that we're trying to build on the site, or how we're going to remove the hazard, or whatever it is about the site. But we need to think about how that data is adding something. And generally speaking, more information about the site reduces the uncertainty. It allows us to make design decisions that can mitigate against future risks. And I think, of course, that's becoming increasingly important as we have to think about the long-term changes in things like our climate and how that's impacting the future resilience of infrastructure. And geophysics has really been applied in two different ways. And this has been outlined beautifully by the past two speakers, but broadly speaking, it's in reducing costs. So providing spatial information that can help us to minimize the requirements of further intrusive investigation, or it's in adding benefit. And that can often be when a site investigation is underway and an unexpected feature is found, maybe that's a mine shaft or a fault that wasn't known, and a technique is needed to come in and really try and better understand that from a spatial perspective. And of course, the question I want to pitch today, and it won't be any surprise to know that I'm going to sort of make the argument that this can do both, is that, can geophysics both reduce cost and add benefit in projects? Now, I talked a bit about remote sensing, and the reason I always talk about this is because I always think that it's incredible the developments we've seen in remote sensing, and as I say, it's really captured the imagination of many people. But as a ground engineer, someone who works in the ground engineering sector, I always think, well, if I was going in for intrusive surgery on my head, what would I really want the surgeon to have in his or her hands before they sort of embarked on their own site investigation? Do they want a high resolution image of the site they're going to be working on? Is that going to be most value to what they need to do? Or do they need to have some means of actually seeing inside and getting an idea of what the conditions they're going to be working with are going to be? And to my mind, geophysical imaging, geophysical investigation provides that unique opportunity to have that holistic view of what's going on the site that we just cannot obtain from remote sensing of the surface or from very, very dense investigations using intrusives. It bridges a scale of resolution and gaps in our information that just cannot be obtained practically using any other means. And to try and sort of, demonstrate how we can approach this, I want to talk about a project I was involved in with AtkinsRéalis. This was part of the Strategic Pipeline Alliance, which is a project for Anglian Water, looking at refreshing hundreds of kilometres of pipeline in the east of the country, including this particular site in Lincolnshire, where Anglian Water were planning to build some very large water retaining structures, primarily a lagoon and a tank. And this was built on Lincolnshire limestone. So anyone who knows the Lincolnshire limestone will know that it's a very heterogeneous rock mass. It's prone to things like dissolution, development of caves and sinkholes, so a very karst environment. And also, because we have a soluble rock, we have these areas where we've got eroded bedrock, which is filled in with glaciofluvial infill, very, very clay-rich material that poses a real risk of differential settlement, especially when we're building these very weighty structures which are going to hold vast volumes of water. And there was also a need to understand the hydraulic condition around ground as well. So if there was an emergency or planned release of water, where was that water going to go? Was it going to exacerbate some of the potential karst hazards on the site? And I should point out that this project started before AtkinsRéalis actually started up its near-surface geophysics division. So this was initially investigated using a reconnaissance geophysical survey that was specified by engineering geologists within AtkinsRéalis. There was a follow-up phase of intrusive investigation. So that's actually the red dots you can see on the screen there on the right-hand side. There was then a survey which we did, and this was after AtkinsRéalis got geophysical specialists in who specialize in near-surface investigations. And then we processed that data, and there was a follow-up series of ground investigation as well, which is the green dots on the right-hand side. I'll talk a bit about what all the red and blue lines are in a second, because it's fairly confused, but we'll walk through the project now, and hopefully it'll all become clear. So back in 2022, the site was designated as one that was going to be investigated to house the potential infrastructure, as I described previously. And we're looking at two parts of the site. We've got effectively a field in the east and a field in the west, and a large-scale electromagnetic survey. So those who've read the guidance or are familiar with geophysics will know that's an instrument which is either walked or towed around the site and gives you this lovely plan image of the distribution of electromagnetic conductivity across the site. That was undertaken across all of the western field and part of the eastern field. And the results of that broadly correspond to the BGS mapping, which is the pink areas you can see underneath on the left-hand side of the screen there. So where we have these pink areas which indicate we have this glaciofluvial clay-rich sediment, we can see particularly on the western side of the site, we've got these blue, very conductive features that indicate we might have a greater mass of clay-rich material sitting in those areas. And to try and get some information about what's going on beneath this, a series of orthogonal resistivity lines was specified for the survey, undertaken at nominally 50-meter intervals across the site. And we can see on the right-hand side there, so this is looking towards the northwest, we've got, generally speaking, more more low resistivity or high conductivity features extending to depth in the north. So that's furthest away from where we're sitting at the moment. And then as we sort of come closer to the screen, we can see there's higher resistivity features indicating perhaps more competent bedrock, lower proportion of clay, something you might want to build on a bit more. And the results of this were intrusively investigated, so a series of 4 boreholes. I'm only showing here the boreholes that were drilled in the eastern field, and the reason for that is because the geophysics alone underpinned the decision to completely move the project towards the eastern field based on the vast volumes of clay-rich material that were investigated and found in the western field. So that instantly was able to inform a design decision that was said, we're going to try and avoid as much risk as we can of this differential settlement caused by potential clay materials and relocate the entire infrastructure project to the eastern field. Great. They then drilled 4 boreholes, which were done at fairly arbitrary locations at pretty much the intersections of the ERT lines, the resistivity lines, which had been acquired in the previous survey. And those 4 boreholes came back logging a sort of broad distribution of limestones, but notably only limestones underneath superficials, ranging from weak through to strong limestones. So the dark colors there on the right-hand side are where we've got stronger limestones logged by the engineers. The lighter blue colors are where we've got weaker limestones. What's interesting is that you can see there's one borehole there to the sort of north, which again is furthest away from where we're sitting, which shows there's this weak limestone sitting at the near surface, but that seems to disappear as we go towards the south. So perhaps not an unreasonable assumption to say, well, we'll relocate the infrastructure towards the south because it looks like, according to these 4 boreholes, we've got stronger ground. It might be more suitable for putting these large water retaining structures on. Fantastic. And then Atkins hired some geophysicists and we had to come and make it slightly more complicated. So we looked at this data and we said, well, that's great. You've got some fantastic data here and it's certainly achieved the brief that was set out. But in terms of mitigating against risk on the site, there are large 50-meter holes in this resistivity data set where we don't know what's going on. And we've already ascertained from our desk study that there's a risk of dissolution. And we're not sure that because these boreholes have been drilled at these arbitrary locations that we're necessarily capturing the entire heterogeneity that is presenting at the site. So we said, we think you should go back to the site and you should do some more resistivity profiles, but at a much, much closer line spacing this time. So we went back and we did this one in-house ourselves. We acquired 15 more resistivity profiles, or 13 more actually. We used 2 of the profiles from the previous investigation and collated those with the additional data we had. So that now, rather than looking at 50-meter separated lines, we were looking at 8.5-meter separated lines. So a much, much closer space survey. And this took an extra 4 days to collect in the field. It was relatively quick to acquire, relatively quick to process, and not too long, a couple of weeks for us to get the results. And the main thing here is that we've gone from having these 50-meter separated resistivity profiles to suddenly being able to produce a model of the site, which is 100 meters by 200 meters and goes down to 20 meters depth, which is a 500,000 meter cube model of the site. In other words, we now have some information from everywhere that we're interested in developing. And you can see on the right-hand side of the screen here, we're seeing a sort of depth slices increasingly going down for this model. And the thing that struck me immediately was the 3 boreholes in the south. They are the dark squares that you can see, almost exclusively intersect resistivity maxima in this plot. So by complete chance, the 3 boreholes in the south, which were drilled, all happen to hit the 3 highest resistivity zones. Now, of course, you've read the CIRIA guidance, or you're going to, but that would, the basic theory behind that is that where you have more competent bedrock, you've got less interference of things like heterogeneous material, clay infill, fractures in which water can flow. That's going to increase your resistivity. So what we think has happened here is the boreholes have overrepresented the amount of rock, or intact, strong rock, I should say, on the site. Because actually, we seem to have these channels and other features where we've got these yellows and oranges, which perhaps are not highly competent and intact rock. So as a result of this, we said, well, look, rather than just use our gut feeling about this, we'll actually have a look at some of the data and see if we can get a bit more quantifiable with our results. So what you're seeing on the screen here are resistivity profiles taken from each of those borehole locations. And the shapes that sit around each of those data points just tells us what the rock quality or what the rock strength is at the particular locations. And I think it's really interesting that you can see as we go towards the right, we've got increasing resistivity, and generally speaking, all of the borehole locations, all of the points in the borehole show medium or strong limestones. I should have said that we started from below the rock head level here. So we're really just interested in the limestone. We've kind of discarded the superficial materials from this because we're aware there's a superficial cover on the site, which seems to be relatively homogeneous in its thickness. There are some deeper areas which are picked up by the resistivity model. But the thing that really stands out here is that in that borehole in the brown color, so the one further to the left, which has the lowest resistivity, we can see that the one instance of low or strength limestone on the site coincides with where we've got low resistivity. Now, a major assumption of this is the statistical significance of saying, right, we have one borehole that has weak limestone and has low strength weak limestone and low resistivity values. We have assumed massively that that is, valid for across the site, if not by anything, just by the virtue that all the other borehole records show medium and strong limestones with higher resistivity. And what we said to ourselves was, well, we're particularly interested in where we might have dissolution at depth or presence of heterogeneity, particularly if we're going to see, for example, dissolution or caves that may crown up towards the surface. So this is our danger zone. We're interested in where we've got low resistivity at depth. That to us tells us that perhaps we've got non-intact limestone or weak limestone at an area which is going to cause lots of problems for the project. And interestingly, we went back and we actually extracted what I'll call virtual boreholes from the data set. So we looked at some of the resistivity minima, and we showed that actually there are areas of this model which have got much lower resistivity results than even the area that was co-located with the weak limestone. So there's good reason for us to think there may be more going on here than just the presence of intact limestone as indicated by the boreholes. So what we did is we took this information and we sort of put it into a 3D model and just tried to come up with a very broad overview of what this is telling us about the site. So there's our 4 boreholes, the 3D resistivity model that we produced, that's the total volume. And as I said, we stripped off the superficials, so we're just looking at what we consider to be the rock head here. And when we start to think about that danger zone I mentioned, we can segment that up using the volume of the 3D model to say, well, this is where we think we might have greater heterogeneity, and this is where we might have lower heterogeneity in the site. And we can integrate that into an overall risk map. And the great thing about this is because we haven't built anything yet, because we haven't started into our detailed design, we can do exactly what we did in the first phase, which is say, well, actually, if there's lots of heterogeneity present in this part of the site, we can just move the whole infrastructure south to an area which we think has got a higher degree of confidence around its strength of limestone. But of course, the ground engineers didn't want to take our word for it. Absolutely fine. They went off and drilled some more boreholes. And in the initial investigation, it was notable that those 4 boreholes came back really showing only limestone beneath the superficials. There was the occasional bit of thin, sort of less than 20 centimeter thick clay infill or gravel infill, but nothing that would be significantly detrimental to the construction of the infrastructure. There was no evidence of dissolution in those boreholes, and only occasional infill staining associated with the fracture showing there had been significant hydrological alteration. In the follow-up investigation, we asked them to drill 5 more boreholes. They're mostly based on the low resistivity features we found, but we did ask them to look at one high resistivity as well, just to kind of get the other side of the picture. And in all 4 of those boreholes that were drilled in the low resistivity zones of the 3D model, there was significantly more heterogeneous ground. So we had, in some cases, over 3 meters thick of zones of non-limestone. That included siltstones and clays. Evidence of minor dissolution in 2 boreholes as well. So we were looking and worried about things like karst dissolution, and we seem to have found evidence of that. And also far more evidence of hydrological processes. So clay infill within fractures, calcite crystal growth, and all the kinds of things that indicate we may have water flowing, perhaps in groundwater flood events through these areas. Which again, I mentioned that because these are water retaining structures, we have to better understand how we're going to manage water in the event of a planned or emergency release. And in essence, we've used this data to really have a much better understanding of the heterogeneity within the site, which has been able to then obviously inform the design decisions. I think Charlotte alluded to this earlier, that the time at which you intervene on these things is really important. So trying to get these types of techniques in early can really help with the design of your projects and with the cost. And I think that's something that as geophysicists we say quite a lot, and often we have to come up with the numbers to try and back that up, which is what I'm going to try and do now. So each of the borehole symbols here represents the cost of one borehole. I mentioned there was a reconnaissance survey that was done initially, and off the back of that, they drew these 4 boreholes at the cost of 4 borehole equivalent costs, we say. And then we came in and we did a 3D resistivity survey, and that cost the equivalent of drilling 2 boreholes. I think it's notable as well to say that, Oliver talked about this, about the quality of information. We have a meter cubed here of information recovered from the ground investigation. We have 500,000 meters cubed recovered from the resistivity survey. And based on that resistivity survey, we had to then go and ask them to drill 5 more boreholes. So at this point, we're up to something like 11 borehole equivalent costs. I mentioned the difference in volume there. I think it's really important to point out that 1 meter cubed of logged core doesn't have the same value to the project as 1 meter cubed of resistivity data. There's no equivalence there whatsoever. But it is, I think, important to point out the cost of 1 meter cubed of resistivity data is 1 million times cheaper than 1 meter cubed of logged core. And it's also really important to point out the environmental impact of this as well. So getting that 500,000 meter cubed model costs 2,000 times less carbon emissions than getting the 1 meter cubed of initial ground investigation data from those 4 boreholes. But importantly, I think if this had been done slightly differently, if we'd been able to do that 3D resistivity from the beginning, before we'd even drilled any boreholes, we might be in a situation where we've got the 3D resistivity, we've then drilled a more conservative number of boreholes, and we can still come to the same conclusions, or maybe we can even hold back some additional investigation boreholes to have a look at once we've drilled the minima and maxima of the model to understand what's causing those sources of heterogeneity. But in our estimation, we're looking at maybe being able to reduce the overall cost from 11 borehole equivalents down to about 8. Doesn't sound very much, but it's a 27% reduction in the cost for the project overall. So I think hopefully that demonstrates, we can both save costs, but we can also add this benefit of having a much better holistic understanding of what's going on the site, particularly when we're able to marry up the geophysics with the ground investigation data to really have a comprehensive picture of what's going on the site. So with that, just a few brief conclusions from my end, which are that I think Oliver alluded to this, I think Charlotte as well, geophysical data are not just planning tools. They are valuable sources of ground investigation data that when managed properly, when specified properly, collected by competent people, and I saw there's a question about that, I'm looking forward to talking about it, that we can really use this information to underpin the decision-making process for our projects. And we can use it just beyond using it to plan our GI or to try and work out what's going on when we have a problem. I hope that it's inherent in this presentation that geophysics done well can both add benefit and lower costs. And I think it's important as well, and I don't think anyone who's spoken today would disagree with this, that the CIRIA guidance is no replacement for a qualified geophysicist. It hopefully gives you a fantastic idea about what we can do with the data, how you can use it, the types of applications. But one of the things I would definitely appeal for is better uptake of geophysicists within ground engineering, making sure that we're consulting with people who have a good understanding of how this data works, the types of modeling processes we use, and really working to interface with the engineering geologists and geotechnical engineers so that we can break down that communication barrier, make sure we're working and talking about the same problems from a unified perspective. So yeah, thank you very much for listening. I just want to very briefly sort of give my thanks to the Strategic Pipeline Alliance Anglian Water Project for allowing us to present this. My co-colleagues there, both within SPAR and also within ACRIMIAS as well. And yeah, very much looking forward to the discussion around this.
Right, thank you, Jim. It's a very interesting talk to finish. We now have about 20 minutes for discussion. So may I ask all the speakers to switch their camera on and your microphone on so that we can see and hear you. Right, wonderful. So we have received a few quite interesting questions. Don't know if your speakers can see it, but I can say it so that everybody can know what it is. He said, now that GPR is a compulsory contractor requirements for PIS surfaces clearance, is any record being kept of numbers of surfaces striked versus GI prior to the new regulations?
If I'm honest, I don't know is the simple answer. I'd like to think that the health and safety executive would be keeping tabs on these things, but I'm not aware of any studies being done.
Yeah, I think my answer would be pretty similar to that, to be honest.
Any June, got anything to add?
Not massively. I'm not super familiar with PAS 128. It's something within Atkins Realis at least is definitely taken care of by a different department. Appreciate that the GPR is a compulsory part of that. I don't know if is PAS 128 a compulsory part of site investigation. I'm not sure that it always is. Oliver, you might be able to speak to that. I think you deal with that more often than I might.
I mean, it's the only part of geophysics which is regulated by that we have to do it. So for borehole clearance, yes, you should be doing PAS 128 operating to PAS 128 standards. If you're breaking ground, again, similarly, you're doing utility clearance to PAS 128 standards. It should. I'd be amazed if it doesn't reduce the service strikes. But I've certainly seen there's a bit of variety in how PAS 128 standards are interpreted, shall we say, by different contractors.
There's still a bit of confusion between people requesting what they say is a GPR survey when they actually mean they want a PAS survey instead. And I don't think people fully understand the difference between the two of them. and the amount of extra work that is required for a full PAS 128B survey or whatever. But yeah, it's probably something that should be being kept on record. Certainly that you know, to record the fact that hopefully the number of strikes is reduced. But yeah, I don't think it's anything that's compulsory in itself.
Okay. The next question, obviously, in a way that's synchronized to what Jim has said and has been mentioned by Charlotte in a talk as well. And obviously, it's not our practice, not just a geophysics things. The question is, how is a competent geophysicist defined? Is it consistent with EC7? Which say, I will go to the details of EC7, but are collected, recorded, and interpreted by appropriate qualified personnel.
So I know the way that this is one of the things that was a fairly hot topic of discussion during the meetings that we had on this document. There's a lot of there's definitions of competent engineers in various standards, but there didn't appear to be any definitions for the appropriate qualifications of a geophysicist. We considered standards such as the BS 5930, the AGS Yellow Book, the CDM regulations 2015, and the ICE guidelines on the effective site investigation, and used all of those to kind of define what we felt constituted a competent geophysicist. And obviously there's different levels of geophysicists, but we kind of focused this more on the senior personnel that would be leading a site investigation, for example. So based on things like the ICE guidelines and the AGS, this kind of defined that anybody who is a geophysical specialist that is expected to lead a ground investigation would be expected to have a qualification such as a degree or a diploma, which would provide them the kind of core engineering and science understanding to be able to understand the geophysics, with a reasonable expectation that that person would likely have some sort of postgraduate specialist degree within geophysics as well. And also, obviously, the CDM regulations require that people working on a site to have the necessary skills, knowledge, and experience within that technique they're applying to then use that within that survey environment. So those are kind of like the definitions we gave to describe what a competent geophysicist should be. I know that the ICE guidelines define a difference between a professional and a specialist and an expert, with a professional being somebody who undertakes a survey, a specialist being somebody who manages a survey, and then an expert being somebody who can take responsibility. But we didn't want to go into those sort of definitions because there's a lot of organizations that may use those terms interchangeably. So that was why we kind of went for more like a definition of a senior person who is leading on a site. Obviously, you're going to get other people who are assisting who may not have exactly the same qualifications as that and won't have the same level of experience, but hopefully that kind of answers the question. Yeah,
and I think in the guide you've referenced the level of experience based on for site leads as well, and obviously we've referenced things like CGEL and C-Science as well.
Yes. Apologies, yeah. Yes, so chartered in by some professional body, and then a required number of years of experience, which obviously you would need to have the chartership anyway. So, yeah.
It's always been quite tricky, I think, for the whole construction industry. You know, what is competence? You know, does users' experience count, or chartership counts? I think ultimately somebody that can carry out the duties at the best of the knowledge, efficiently, and obviously able to keep up to date sort of good practice as well. I think that's really important, and hopefully this report will encourage people to have the extra step.
I think for me, one of the key ones is having enough competence of different geophysicists who can review within an organisation, and I certainly find that I find an awful lot of benefit from, we have multiple senior geophysicists with similar levels of experience to myself. If I'm writing a scope, I'll always have that reviewed by somebody else who'll challenge what I put forward and question things, because that getting that balanced view is important, because not all sites are quite as simple as you'd think.
Yeah, it's having that experience, but in a relative in that
relevant
same area. Yeah, that relevant. That's the word I was looking for. Sorry. Yeah, in a relevant area. Which I think Aska's said something about that anyway. So yeah, exactly. A PhD in hydrocarbon geophysics exactly does not give the best perspective on an archaeological geophysics survey. Yes, well put, Aska. Yes.
And I'll just jump in as well with my experience. I mean, I spent 7 years. I did geology as an undergrad because I wanted to avoid doing any sorts of maths or physics at all, which is massively backfired because otherwise I wouldn't be sitting here. But I took 7 years to on site, putting electrodes in the ground and swinging hammers and working up towards processing data and understanding how these things work before I thought, well, I'm going to go and do a PhD in this, which I don't recommend to anyone as a means of really trying to tackle how you understand a subject. But I think, I would say this, obviously I'm biased. I think there is a massive amount to be said for field experience, for having that mentorship of people who maybe do have that understanding. And I think that geophysics, particularly near surface geophysics, is one of the most multidisciplinary approaches, really, or subjects that you can come across. You have to have an understanding of physics. You have to understand how that physics won't work when you apply it to a very messy applied environment, i.e. the outside, the real world. Unlike our deep earth colleagues, it's very easy to get the ground dug up and proven wrong. There's these fantastic papers about what's going on in the moho or in the core, using sort of seismological evidence, but you're never going to dig that up to prove them wrong. Whereas if I say, oh, there's a mine shaft there, but it turns out to be a bit of sheet metal, you can very, very quickly say that I'm wrong, in the cost of one trial pit. As well as that, you have to have great communication skills to be able to communicate some of these very subtle and sort of, delicate ideas around, are we collecting data? Are we presenting models? There's obviously the modeling process as well, understanding data. There's a huge amount of skills comes into it. And I think Oliver's summed it up. No one person really can have the expertise to oversee all aspects of this. It's, I think, very much you need to know where the limits of your expertise are and know where you have to call in other people to be able to provide that gap in your knowledge. I think I've answered similar questions before by saying, well, I may not know the knowledge, but I know where to go look it up. that applies in this field as much as anywhere else. And, thankfully we have things like the CIRIA guidance, which can help with plugging a few of those minor knowledge gaps, at least.
Okay. There's another question, obviously more focused on Jim. The question is, you compare the relative costs for 3D resistivity survey for only one eastern portion of the site. How does the initial 50-meter space survey factor into the relative costs for the project? And without this, would the 3D resistivity survey have been completed over a larger areas of the site?
Yeah, it's very interesting. I think Oliver alluded to this in his talk as well, that this phased approach to how we use these techniques. So in terms of the cost spectrum for what I presented in my talk, you have something like an EM survey. As I said, it's walked or towed across an area, very, very quick to acquire data. Maybe doesn't give you much information in the sense of a three-dimensional picture of the site unless you're going to use very advanced techniques to understand it. And there are similar techniques out there like time domain electromagnetics that could give you that information. But you're looking at that as being the quickest and easiest thing, perhaps then going to looking at 2D ERT to better understand what's going on beneath those areas before you might commission a 3D survey. I think the way that I presented it is by virtue of the fact that I wasn't involved with the project from sort of conception to finalization. But you are right, it would be, I probably should include the initial reconnaissance costs in there. I don't think they would be anywhere, you're probably looking at the cost of one borehole. It certainly wouldn't be more than the cost of the 3D ERT. But of course, we did reuse some of that data in our 3D model. So we weren't duplicating data, we were just adding to the data set. I think if the project had come under my sort of my jurisdiction from the start, I would have still commissioned an EM survey across the entirety of the site, but I might have been a bit quicker to make that recommendation for a 3D survey if not based off just the EM results, perhaps based off 1 or 2 resistivity lines to prove that it was a depth of clay in that region, which would have been a relatively inexpensive operation. And I would have made sure that those lines could have been designed to still be included in the 3D survey later. So lots of ways that we can design that survey from a reconnaissance through to forensic application to make sure that it's still hitting that cost benefit scale that we're so interested in.
Okay, that's interesting. Probably the final question now that we're sort of going towards 25 minutes past 3. There's a question about how much is downhole geophysics covered in the guide. There are a lot of different methods that can make the most out of a drilled boreholes. So obviously some people are still into borehole investigation.
Yeah, I did briefly touch on the borehole geophysics element within my presentation. As I mentioned, it's a massive topic, especially when you include things like wireline, which is why there are standards that exist already for that topic. And if we'd have gone into more detail than we did, it would have been an entire document in itself. So we didn't go into a huge amount of detail. The detail that it does go into is referencing the relevant documents within the section that can be referred to for things like wireline or crosshole, including the ASTM standards and things like that. And then the example given was just one simple downhole survey that was used to look at non-aqueous phase liquids within a borehole structure. But that's pretty much all that the in terms of geophysics within a borehole that the document covers, because there's already so much out there that talks about it, basically. I don't know if Ollie has anything to add.
No, I agree. I mean, it's one of those ones which it would have been, it's such a substantial part of engineering geophysics as well, but it's almost a subject in itself.
Mm-hmm.
So we made a call based on how much we could do within one guide, and to not focus on that one.
Mm-hmm.
Sounds like it could be the start of the next CIRIA guide.
Absolutely.
Yeah. Well, on this rather cheerful note, I just want to sort of quickly summarize about what we talked about this afternoon. Obviously, as a non-specialist but the project manager of a sort of specialist subject, I think I'm still learning quite a lot from today's talk. As I said, I think people seem that there are obviously there are more cases where geophysics actually can add value to projects. I think the industry needs to have better understanding of the benefit, and hopefully the new guide C812 would help to achieve that more. I mean, ultimately, as several speakers has said today, ground is a heterogeneous place. It's very difficult to completely understand everything about it. I always think that unless you got, Superman's eyes, it's almost impossible to do that. So hopefully, as I said, CIRIA is very keen to do more, especially after this report is produced now, to perhaps look into the issues a bit more, how we actually encourage uptake of good practice. As I said, just before I finish, obviously I want to thank the funders and the project steering group members to make this project possible. And obviously I also want to thank the speakers for the excellent presentation today. But most importantly, all the audience, yourself, who's actually able to, who come to this meeting. If you have obviously any feedback, and we obviously CIRIA is very keen to hear from you about what we can do next. As again, the presentation will be circulated to you later on after the event, provided the speakers are happy with it. And last but not least, this is details of where you can get hold of the report. We're doing some sort of Delic's special offers discounted as well, so you get 20% off, I believe. Let me just go. Okay, is it not clicking? Okay, so I think probably that is all I'm going to say today. And as I said, thank you very much for attending this event, and I hope you find it interesting. And as I said, if you come up with any question after the event, any ideas or any reflection on what we can do next, please let myself and CIRIA know. So thank you very much again, and have a good afternoon.
Thank you, everyone.
Thank you. Thank you.
Thank you very much.
Thank you.
Cheers.
Thanks.
Bye.